Now the next point, which is again a very important, what is that thermal expansion? Yeah, so obviously it get expanded when you provide some heat to that. So now there are different kinds of expansion that we have to do, or we have to find it over here. The first one is a linear expansion. So the first one we are calling it as a linear expansion. So in case of linear expansion, I have just considered the rod, obviously, which is a one dimensional. When you provide the heat to this rod, it is going to expand. Let's say it is going to expand in this way. Then what you have to find over here, this L0 is the original length, and now finally the length become at a particular temperature, that is LT. So what it has been found, LT minus L0 is directly proportional to the original length, because if original length is greater, then more part of that rod is supposed to get the heat. So this LT minus L0 is directly proportional to L0. Again this LT minus L0, again you can say that it is proportional to change in temperature. Yes, so obviously if you heated that rod through a, that is a high temperature difference. So initially let's say it is 100 and you heated up to let's say 200. Yeah, or if it is initially 0 and if you heated up to 100, so definitely the length it will get expand more. So LT minus L0 is proportional to delta T. So combining these two statements, if I just combine these two statements, then this LT minus L0 is proportional to your L0 into delta T. Then this LT minus L0 is equals to alpha L0 into delta T. So then again LT is equals to L0 plus alpha L0 delta T. So take L0 common, yeah, and 1 plus alpha delta T. So this is your LT. Fine. So this is how we can just find the length of that rod at a particular temperature with the given formula. So this alpha is called as a coefficient of linear expansion. This is what we can say as a coefficient of linear expansion. And one more formula you can say, so obviously this is how we can, this alpha again it is defined as the change in the length per unit original length per unit rise in temperature, and the unit also you can say for this, so this is per degree Celsius or per degree Kelvin. So that is your alpha, coefficient of linear expansion. It is defined as the change in the length per unit original length per degree rise in temperature is nothing but your alpha over here. Now the next one, let's say if I just consider the areal expansion or the expansion related to that area, so that is also called as a areal expansion. So I'm having one square, yeah, now just I'm heated it, you have to just provide the heat, it is going to expand from all the direction. So obviously the new surface area is AT, initially it was A0. Similarly you can write it down, this AT minus A0 is proportional to A0. Then again this AT minus A0, again similarly it is proportional to delta T. Now combining these two statements you will get obviously which is A0 into delta T. So again just remove that proportionality constant which is beta A0 into delta T. So this AT minus A0 upon A0 T, yeah, delta T, that is beta. So this is how we can define the coefficient of your areal expansion, yeah, or superficial expansion. So this is finally again AT is equals to A0 1 plus that is again beta into delta T. This is also how you can write it down, that is a change in the area per unit original area per degree rise in temperature, that is a coefficient of superficial expansion. Yeah, so the next one also you can define in the similar way, that is a cubical expansion. This is the third one, is the cubical expansion where the volume is going to change. Let's say this is nothing but the cube. Now when you provide the heat to this cube, obviously this cube is going to expand in all the direction. So the volume is going to change now, the volume is going to change. So this Vt minus V0, again you can say that it is proportional to V0. Again this Vt minus V0 is proportional to delta T. So combining these two statements this Vt minus V naught is proportional to, again I can say, V naught into delta T. Then this is Vt minus V naught, again this is gamma V naught delta T. That gamma is nothing but coefficient of cubical expansion, and this Vt up minus V naught upon V naught into delta T is equals to gamma, that is a change in the volume per unit original volume per degree rise in temperature. Or this one Vt is equals to V naught 1 plus gamma into delta T. That is also how we can define that your volume at a particular temperature is given by this particular formula. So this is what we had defined for your starting from your coefficient of linear expansion, alpha, coefficient of superficial or areal expansion, or the third one is nothing but the cubical expansion. So that is the formulas, and that definitely the equation for all of them. Now let's see the practical application of your thermal expansion. So if you've seen that your rail tracks, there is a small gap in between those rail tracks. So why we are keeping that difference in that gap between those rail tracks? So it is for your expansion. Yeah, so during the summer that your definitely that your rail tracks will get expands. If you don't keep that, you're definitely the gaps over there. So you can see that. So this is how those rail tracks looks like, and there is a possibility of accident of the train, it might get derailed. So we have to just keep a small gap over there between those rail tracks, so it will get expanded over here and it doesn't harm. Yeah, so that is why we just keep those small gaps, so which is the application of your thermal expansion. So now keeping just the next one is the variation of density with temperature. So for this case we know that, so we have seen that Vt is equals to V naught, again 1 plus gamma into delta T. Yeah, or let's say for example that is a T over there. Again we know that rho is equals to mass upon volume. So according to that, so volume is equals to Vt, let's say, upon your rho. So which is, again I can say for this particular case, so this is how we can just write it down over here. So this is for example m upon your rho T, again this m upon that is a rho naught 1 plus gamma into T. So this get cancelled. Yeah, and again obviously we can say for this case, so this one I can write it down. For example, just take now that is a cross your product. So rho T is equals to rho naught. Yeah, and 1 plus gamma T raised to minus 1. So this rho T is equals to rho naught 1 minus gamma into T. That T is nothing but change in temperature. So this is how also we can write it down, the density at a particular temperature. So this is the variation of density with temperature, and the expression for the same you can write it down, that is a rho T is equals to rho naught by just taking this cross product, and we can write it down, that is a 1 minus gamma into T over here. So one more thing we can say over here for this particular case, let's say for example, so alpha, the relation between, so you can find obviously the relation between that alpha, beta and gamma. So alpha is equals to given as a beta by 2 is equals to gamma by 3. So this is how we can define the relation between alpha, beta and gamma over here for this particular case in that. Yeah.